So now let us see Kolbe's reaction. So here Kolbe's reaction, it is also known as Kolbe-Schmidt reaction. It is a carboxylation reaction as well as electrophilic aromatic substitution reaction. That is, here an electrophile is substituted on benzene ring, that is an aromatic ring. So here let us see a reaction where we will be taking phenol, it reacts with strong base which is sodium hydroxide, will give us sodium phenoxide. Now this sodium phenoxide first reacts with carbon dioxide and then reacts with H plus, will give us two compounds. One will be our major compound and the other will be our minor compound. Major one is salicylic acid. It is also called as orthohydroxybenzoic acid. Why do we call orthohydroxy? Because here priority wise we are giving first priority to carboxylic acid group, which is COOH group. So then these groups, these positions of benzene ring are considered to be ortho position, meta position as well as para position. That's the reason why we are saying orthohydroxybenzoic acid, and this is para hydroxybenzoic acid is considered to be our minor compound. Now let us look into the mechanism of this reaction. So first here we have taken phenol. Here phenol, oxygen, as it is highly electronegative, it will take electrons from hydrogen, leaving hydrogen as H plus. Now this phenol, as I said here, it is reacting with strong base NaOH. The H plus will form a bond with negatively charged hydroxy group and will leave as H2O. Now this Na plus and O minus will form sodium phenoxide. Now here, as we are having a phenoxide ion, it will show resonating structures. So these are the resonating structures of phenoxide ion. That is, you can see negative charge is shifted over here, then the double bond which is present over here will form a negative bond. In the same way, cyclization is seen. The pi bond is shifting at various positions over here, and finally again we are getting our phenoxide ion. So now here in this compound, so here you will be getting in resonating structure, you are getting one of the structure over here. So with this structure we are reacting our carbon dioxide. So here again oxygen, it is highly electronegative, it will take the electrons from carbon, leaving carbon positively charged, and this oxygen here will get a negative charge. Now to this positively charged carbon, here the negative charge will form a bond with this positively charged carbon, forming a CC sigma bond. Now here you will be having a hydrogen. Now this hydrogen, what it does, it will donate its electrons, forming a pi bond over here. Then oxygen will take the electrons, getting a negative charge. Now this negatively charged oxygen will form a bond with this positively charged hydrogen, forming a hydroxy group over here. Now this is salicylate group. As we are having a negative charge on oxygen, it is a carboxylate group, and the whole compound is salicylate group, salicylate compound. Now this salicylate in acidic medium will give us salicylic acid and para-hydroxybenzoic acid. So this is the mechanism for our Kolbe's reaction. Now where we can see Kolbe's reaction? So here this is an example for Kolbe's reaction, where we will get to see here catechol converting into 2,3 dihydroxybenzoic acid. So this is catechol, which is also called 1,2 dihydroxybenzene. It will react with carbon dioxide first in basic medium as well as in acidic medium, will give us 2,3 dihydroxy. So here priority wise again we are giving first priority to our carboxylic acid group. So this is our first position, this is 2, 3, 4, 5 as well as 6. So 2,3 dihydroxybenzoic acid. So here you will get to see the mechanism for Kolbe's reaction. So this is what called Kolbe's reaction.